All right. So data center networking issues. The first is that oversubscription is an issue. We have in the same rack there is no oversubscription generally because you just get 1 gigabit and 1 gigabit out to the switch. But from the switch onwards you have 1 to 2 to 1 to 20 oversubscription. For example, you might have 32 times 10 gigabit down, but only 8 times 10 gigabit up, which is 80 to 320, 4 to 1 oversubscription. Core routers are oversubscribed with 1 to 240. 240 times more traffic can come in than it can get out. Right? So generally so basically your idea is that you want to really keep people who are talking too much together. Because if they have to talk over the backbone, then backbone is already oversubscribed. It will be a big problem, right? So you want to put services which talk to each other in the same rack. Either that or you change your network. So a lot of people are doing research on how to change the network so that anybody can talk to anybody. Right? So moving across subnets is painful. But that's another problem, is that Ethernet is good, IP is bad. And you will hear this lecture all the way through this IEEE and throughout the data center thing, because Ethernet made few decisions early in the game which really are helping now 40 years later. IP made some decisions early in the game which are hurting us 40 years later. And one of the decisions is how to address things. Ethernet addresses by the name, IP addresses by the location. So your IP address is row 3, row 2, chair 4. If you move to that one, your IP address changes. Big problem. Your Ethernet address is fixed. Whatever your name is, that is your Ethernet address. You move there, you are still the same address. You move there, it is still the same address. I can still send a packet address to you, you will get it. So the Ethernet does not care for the location. It just gets the packets to the right place. And that's big advantage when you want to move the virtual machines around. You can move any service to any other place. But if you don't go to layer 3, we are all happy because it will get there. If I have to go through layer 3, then I have to find your location. So moving across subnets is painful, requires reconfigured IP addresses and VLAN trunks and so on and so forth. What is VLAN? Virtual LAN, and I have a whole lecture on that one right now. I don't know whether we taught you in 473 or not, but since this class is on virtualization a lot, I thought I will put at least few slides. So I have VLAN. So anyways, this is very difficult. So basically, some services trample on each other. Overuse by one service affects others. The second thing is because of the oversubscription, everybody affects everybody else. If you are oversubscribed, there is only 1 gigabit and 240 people are trying to get in. What is going to happen? Somebody is going to be killed. Right? It better be not you. And so that's another problem. Poor reliability. One access switch failure doubles the load on the others. And so now we want to design network topology that will not have these problems. We already saw that whatever traffic is coming from below, more traffic is coming in and less going out. Right? And the ratio is called oversubscription. So for example, you might have 32 10 gigabit down, only 8 times 10 gigabit up, and that would be 40 up, 320 down, give you 4 to 1 oversubscription. Core routers are 1 to 240 oversubscribed. In the sense that if you have a core router, they might have 240 servers underneath, 2 tiers down, each of them with 1 gigabit, but the core router has only maybe 1 gigabit out. Alright, so 240 can hit it, but it cannot really serve all of that. So that is basically the reason that you don't really want to go through the core routers as much as you can. If you want to go from one server to the next server, you want to keep them into the same tree, same part of the sub tree, which is same part of the layer 2 tree, as much below, as close to, so basically you want them to be as close as possible. Now there is a problem with that. So if you have oversubscription, then you cannot just move servers anywhere you want. So you cannot move from here to that part of the data center. That restricts us, right? So there are ways to take care of that problem later on. But right now, from the concept that we have learned in this class, This is a problem. Service trample on each other, and so because of moving across service is painful, requires reconfiguration of IP addresses and VLAN trunks, and that actually is the problem with IP. IP was not designed with more mobility in mind, and so it just indicates the location, and therefore every time you move you have a new IP address, and that creates a problem. Now people have to figure out how to get to you. With Ethernet that's not a problem because you keep the same MAC address. Services trample on each other because if there is a bottleneck, then if one service uses more, then the other service get less. That's a problem, right? And so we need to fix that. Poor reliability. Now we have two access switches, but if one fails and you are using both, then the over subscription on the other one goes up by a factor of 2. Hopefully you are not using it, then you are losing money anyway, because if you are not using it, you have paid for the 2 but you are using 1. So that's not good either. So we somehow want to be able to use 2 and not overload. Underutilization is that oftentimes we don't use multiple paths, we just use one path. So one thing which is kind of a standard and becoming a standard and is, as we talk about in the next lecture, that we use is ECMP, equal cost multipath. Equal cost multipath means that if somehow the switch knows that there are two paths to the destination, left and right, and they are both same cost, then it will try to send 50% of the traffic this way, 50% this way. And that way you are basically not congesting the shortest path. I mean, actually the question in this case is there are two shortest paths. Right? So you're not congesting one shortest path. Everybody understands ECMP? ECMP is equal cost multipath. So equal shortest cost. Other issues are underutilization. That we are not using all the paths. Everybody is taking the shortest path, and that's a problem. You were told in 473 the shortest path is best. Right? But if everybody took the shortest path, what will happen? It will be congested and everything else is free, empty. Right? So we don't want to do, we want to do something different, right? So multiple paths exist, only one is used. Even if there are multiple shortest paths, we don't use parallel paths, we just use one. Well, when the latency is issue, but then you have to worry about the congestion, because latency is the one that affects the congestion, and if it is unloaded, if it is underloaded, then yes, shortest path is good for latency.
All paths are almost equal always.
Okay, no, hold on. That thought, keep up with that thought, because that is not true. But what we do is, if there are two paths which are equal, then we do ECMP, equal cost multipath. So that is what is common nowadays, both at layer 3 as well as layer 2. Ethernet as well as IP both will use ECMP, which is equal cost multipath, which means that if there are two shortest paths, half of the people will take this, half of the people will take that. First statement you made is that all paths are equal. That is not true. If you are going from this rack to this rack, that is a short path. If you are going from this rack to that rack, this is a long path. We are talking about the latency, about the levels of the packet sizes here. The latency here is 3 packet sizes, because the queue is 3 packet sizes. You're going through only one switch. Over there, going through 2 switches. So I think the difference matters. So basically, the idea is that ECMP is used. I think I will stop right there. I really encourage you to read that book, and because there's no way I can cover everything in this class. You really have to read to find all the detailed information. Okay? And all the references are there. Every page I have tried to put the references. Every figure there is a source underneath, so you know where it came from, where I got the information, and so please do. Okay?